Part 3 of chapter 14 is all about splitting, okay, which is summarized on this slide here. Okay, slide 32 by my count. And this is something that's really fascinating and incredibly useful about NMR. Okay. When we actually resolve these peaks, if it's low resolution, everything's just showing up as one kind of broad peak. But with enough resolution, we see that these signals actually split a lot of the time. Okay? Either it's just one sharp line known as a singlet, two lines of the same height known as a doublet, okay? Three lines in a 1 to 2 to 1 ratio known as a triplet, and then four lines 1 to 3 to 3 to 1 ratio known as a quartet. Okay? There are other examples as well on past that, and note those we just refer to as multiplets. Yeah, anything more than a quartet we would refer to as a multiplet. And this phenomenon with these signals is called splitting. Okay? And why does it happen? Well, it has to do with how many proton neighbors we have. Okay? Really useful thing about NMR. Okay? That splitting pattern will tell us how many neighboring hydrogens we have. Okay? Which is that's an important idea to have in your notes, right? Splitting isn't caused by how many protons are producing the signal. Splitting is caused by the number of protons that are bonded to directly adjacent carbons, okay? Also known as the N+1 rule. Okay? The number of peaks in a signal is called the multiplicity. So over here, for example, this is a doublet, the splitting pattern. The multiplicity is 2. It's a doublet. Over here, this is a quartet. And another key thing to have in your notes, right? They have to be non-equivalent protons producing the signal that are causing the splitting, rather. Okay. So chemically identical protons will not split one another. So let's look at this spectrum here. For dichloroethane, we have a unique signal for this hydrogen, and then a unique signal for these three hydrogens. Okay. Now this hydrogen right here, okay, closer to the chlorines, thus it's appearing further downfield. That's the signal over here. That hydrogen has three neighboring hydrogens. 3 plus 1 is 4, which is why this signal appears as a quartet. These hydrogens produce the taller signal further upfield here. Notice the integral, 1 to 3, right? That integration from video 2. And these three hydrogens have one neighboring hydrogen. 1 plus 1 is 2. That signal appears as a doublet. Okay. So again, the multiplicity is the number of peaks in a signal. And it's a phenomenon that's always mutual, okay? Because if those hydrogens are neighboring, they split one another. If A splits B, B also splits A, like we just saw. Those are called coupled protons when they're bonded to adjacent carbons. And I already referred to this. Oh, sorry. Going back. The number of protons that are producing the signal doesn't affect the splitting at all. Okay? It's the number of neighboring carbons, looking both ways, both to the left and the right. Okay, or top bottom, depending if we have multiple carbons. Look at all of them. We'll talk about the number of bonds away in just a second. A couple of things for practice here. Okay, I recommend you pause the video. This is if we're in a face-to-face class, we would talk about each of these in turn. Pause the video right now, predict how many signals you would get. Well, it's kind of a given away here because they're labeled A, B, and C, but predict how they would be split. I'm looking at the answer. A is a triplet right here. Okay, because it's split by these two neighboring hydrogens. 2 plus 1 is 3. B is a quartet. Okay, 3 neighboring hydrogens plus 1 is 4. So the hydrogens for B appear as a quartet. Over here, C, there are no neighboring hydrogens. Okay, so it just appears as a singlet. Here's another one. Okay, pause the video. Predict the answer. And here we go. A triplet, 2 multiplets, and a triplet. Okay. Looking right here for A, right? 2 neighboring hydrogens, 2 plus 1 is 3, is a triplet. Okay. B and C Okay, B right here has 2 plus 3, 5 neighboring hydrogens. So that would be a factor of 6. So we just call it a multiplet. Over here, right, C has 2 and then 1 over here, right? It's going to appear as a multiplet, and we'll talk about why it's not just a quartet in a little bit. Okay, and then D is a triplet, right here. Make sure you're thinking about everything that's going on. D is this hydrogen here. The neighboring carbon has 2 hydrogens, plus 1 is 3 for a triplet. And keep in mind what I mentioned before. If the protons are identical to one another, they don't show splitting, which can be tricky. It's a little tricky thing to look out for. Okay, here, no other neighboring carbons to worry about, or neighboring protons, excuse me, right? So no splitting that we would even anticipate. Over here, we might think for a second that these neighboring 2 protons would cause the signal to have a triplet, right? Appear as a triplet. But the protons are chemically identical to one another, right? Because that's a symmetrical molecule. Equivalent protons do not split the signals, so this would just show as one big singlet because those are chemically indistinguishable, chemically identical protons. So what causes splitting to begin with, right? Why do we actually see this phenomenon, right? It's something known as spin-spin coupling. When we have 2 different kinds of protons that are close enough to one another for their magnetic fields to influence one another, they can do it in one of 2 ways. They can either align with one another to add to the applied magnetic field and cause it to go slightly downfield, downshifted, or they can be directly opposite and subtract from the applied magnetic field just a little bit, causing it to appear further to the right, upfield. So whereas our normal signal would appear here if it was undisturbed, the neighboring proton, right, can appear aligned, causing it to just go to the left, or opposite, just to the right. Okay? So that's if we have one neighboring hydrogen, right? One of 2 possibilities. Now, what about the other way? Okay? If we have 3 neighboring hydrogens to get a quartet, there's a bunch of different ways that those things can possibly line up. We have to consider the different combinations of all 3 of the magnetic fields from those hydrogens. And this is a really good slide at showing it. It's a 1:3 to 3:1 ratio. And the middle peaks are higher because they're more probable to attain. Right? It's more likely to get combinations of 1s and 2s than it is to get all 3 aligned with the magnetic field or all 3 against. Okay, so splitting, that spin-spin coupling, is just slight magnetic fields on the applied, slight effects on the applied magnetic field. Again, for hydrogens on adjacent carbons. The number of bonds away is what dictates whether or not coupling is present in the first place. Okay, this is another key thing for your notes. Splitting is observed if the protons are separated by no more than 3 bonds, okay, with one exception you see there at the bottom. Okay, splitting has to do all about bonds, nothing about space in 3D. Okay, because otherwise rings and bended protons, you would see splitting there, right? The splitting we're thinking about here in NMR, just about the number of bonds away. So these 2 protons will split one another because they're exactly 3 bonds away. 1, 2, 3. Okay, these guys don't because they're 4 bonds away. 3 total bonds. And that's really what we're going to be dealing with, this type of example. I don't want to say that's an absolute because sometimes splitting does occur through 4 bonds only if one of them is a double bond, like we see over here. That's called long-range coupling. You see it with alkenes or alkynes, not something we're going to talk about further. This is what we're concerned with for the purposes of my class on the left. Okay, exactly 3 bonds away. Okay. So for the rest of this video, there are examples for practice. And again, I'm going to encourage you to pause these things and make sense of the spectra. Yep. Let's look at dibromopropane, for example. This is one to talk about. Consider the structure, the peak position, and the splitting. Yep. So we have our 2 sets of chemically different protons. Our methylene protons in the middle and then the ones on the end. Make sure you're thinking about this in 3D, right? They're both labeled B. You can see they are the same. They're both bonded to the methylene and the bromine. These ones on the outside are further downfield, further to the left due to their proximity to bromine, okay? Which means A is further upfield to the right. So we get two signals. Our integration should be in a 1:2 ratio. Okay? It's 2:4 overall, but remember it's the simplest ratio. And sure enough, we see that 1:2. Now, what should our signals be? Okay. Now, your B protons here are both split by the middle protons. So they have two neighboring hydrogens. 2 + 1 is 3. That's going to appear as a triplet. Okay. So this is B right here. Right. This is the signal. This is it blown up so we can see it in detail. And the A protons are split by the hydrogens on each side. So 2 here, total of 4, n + 1. 4 + 1 is 5. Right. So that appears as a multiplet over here with 5 peaks. That's what we're looking for. That's all the information that NMR gives us, right? It's really a wealth of information if we know how to use all the different tools. Okay. So for the next couple of slides, pause the video on the structure, figure out everything that you would anticipate seeing, count the number of unique peaks, figure out what the integration should be, and determine what the splitting pattern is. Here's the structure, right? Give you a chance to pause the video. Here's the spectrum. Okay. Giving you a chance to pause the video again to examine it. Right? It's a really useful time to look through each one of these. Don't let the extra peak at 0 over here throw you off, right? Remember from video 2, that's tetramethylsilane. That's just the reference compound. It doesn't affect your structure. Here's another one, okay? Now we're going to do it the other way, okay? Notice I've grayed out the structure here. Now take a minute, pause the video here on slide 47, take the spectrum and determine a possible structure that you could have. This is not something I would expect you to be able to do on a test. I would also give you the mass spec in the IR. Okay. But what you could do, right, is consider how many unique peaks you have and start to figure out the neighboring atoms, right, from the splitting. So we have a multiplet here, then we have a doublet, then another doublet, and then another doublet, which gives us a lot of information. Okay. So pause the video here, think about what you might work with. Then take it a step further. Say I gave you the molecular formula. For this one, it's C3H5Br. If you can take that information in this spectrum, okay, and draw the structure out, you're really going to be well on your way here in chapter 14. Okay. So here's what the structure is right there. Okay. The challenge here would be determining the presence of bromine, which would be easy to do with mass spec from chapter 13, and the alkene. Okay, but given the formula C3H5Br, right, it would, you would tell that you're unsaturated. So that's, you see how we use all these tools together with one another. What I want to draw your attention to, right, is that notice the protons here, B and C, are not the same. That's because that alkene locks us into 3D. We talked about that in the first video, or maybe the beginning of the second one, right? This does not freely rotate, meaning C over here with the closer proximity to this group is different from B. So 4 unique signals. Okay. So B and D right here are coupled with one another, and they're both still split by C. And B will be split by C. Okay, it's up to a maximum of 3 bonds away. This one's only 2, but it's still getting split because they're different from one another. It's called geminal coupling, okay? Mutual splitting of signals of 2 non-identical protons bonded to the same carbon. A little harder than anything I would give you on a test. Oh, sorry. But really good practice to put these concepts together. So that's where we're going to finish this video off. I recommend, right, go through, rewind, do those things for practice until you're comfortable with all these ideas. Okay? And we'll continue the discussion of splitting patterns in the next video with some other funky things we can see here, known as a doublet of doublets. Okay? But don't worry about that next. This is really, through these first 3 videos, the foundational ideas of IR, that was a whole different chapter in 13, of NMR, before we start to get to some of the exceptions in video 4, and then carbon NMR in video 5.